Okay, so hello everyone. Welcome to week 2 of Math 1510. So the reason we switched to Zoom was because I was having technical difficulties in the previous lecture with BB Collaborate, and because several students said that they prefer Zoom because they can see each other. So now we can see several of the students. The lectures are still going to be recorded, but they're going to be available on YouTube instead of on BB Collaborate as part of my attempt to become a YouTube superstar. So share with your friends and hashtag or like, or I don't know what you do on YouTube. Let me do a quick reminder of what we've seen in the previous week. So in the previous week, we started talking about the multi-layer perceptron network. Oh, 1 second. Oh, sorry, there's a student in the other on BB Collaborate, so I'm just guiding the student. So in the previous lecture, we talked about the multi-layer perceptron and about the forward pass and the backward pass. So this is the multi-layer perceptron. You have fully connected layers followed by a ReLU nonlinearity. And here are the equations, right? So you start with X, which is your vectorized input. And then you multiply X by a weight matrix and you add a bias afterwards, and then you get Z, which are the pre-activations. Afterwards, you apply on Z the nonlinearity sigma, which is the ReLU, which applies max with the zero scalar element-wise, and then you get HL, which we called features. And this is iterated several times until we get to the last layer and we get the logics. Now, a student emailed me saying the following. So the student said, I've glanced over papers that make certain claims around breadth, width, being more critical factor in terms of performance and accuracy in the field. And then the student asks, what is basically depth and width in terms of the multi-layer perceptron we're talking about? So width, when a person says width, they mean L, capital L here, right? So it's the number of iterations that you repeat this process. And when they say, oh, sorry, this is depth. And when they say width, they refer to the dimension of the fully connected layers. So it is often the case that these weight matrices are square matrices, which are of size, let's say 1000 by 1000. And when a person says width, they mean that the size of these matrices is of size 1000. Does this make sense? Now, in the previous lecture, we also discussed the backpropagation algorithm, and we saw these equations that are written here. Since then, a student has emailed me and said that these equations were a bit sloppy because there is transposes in, I guess it didn't use the proper conventions of differentiation. So I updated the slides, and here are the updated equations. I just want to mention that if you're differentiating a certain scalar with respect to a certain, let's say, matrix, then the size of this is going to be of the size of the matrix transpose. So if the matrix is, let's say, M by N, then this derivative is going to be N times M. That's an M on the right? So the dimensions are being switched. And that's the convention that is being used in all of these equations. So for example, when I write here derivative of the loss with respect to Z transpose. Z transpose is a row vector. And so if you differentiate a scalar with respect to a row vector, you get that this is a column vector. Okay. Now, why do we care about these backpropagated errors, or what are backpropagated errors? So backpropagated errors graphically can be seen here. So you start with the loss, which is this thing, and then you calculate the derivative with respect to the output of this fully connected layer. And then you calculate the derivative with respect to this ReLU. Basically, you keep going backwards, right? And then you calculate the derivative with respect to this fully connected. So basically, the derivative with respect to this thing, and so forth. So you keep calculating the derivatives with respect to the different edges here, right? Now, why are we doing this calculation? Because if we know the derivative with respect to these different pre-activations Z, so if we know, for example, the derivative with respect to Z3, then based on this derivative with respect to Z3, we can write the derivative with respect to the weights and bias of this layer. So the first step is you calculate the backpropagated errors, delta 1, delta 2, delta 3. And once you know all of these backpropagated errors, you can calculate the derivative with respect to the weight matrix and with respect to the bias. So here's the equation. So for example, the derivative of the loss with respect to the weight matrix is equal to the backpropagated error multiplied by the features, right? So it's a very simple outer product. Now, people usually like short notations, so they denote the backpropagated errors by a delta L. And then you get these simple equations. So dL to dZ transpose is the backpropagated error, and we denote it by delta L. And the derivative is backpropagated through this equation, right? So this equation is basically saying that you start with a backpropagated error at a certain layer, you multiply by the weight transpose, you multiply by the mask, and then you get the backpropagated error at a previous layer. Shouldn't there be a laser or something here? I feel like I should use a laser. Oh, nice. Okay, we now have a laser instead of, wow, very cool. So this is the backpropagated error. And then notice the derivative of the loss with respect to the weights is just the outer product of backpropagated errors with the features. Does anyone have any questions? No question? Okay, so here's example. Here's how this works in PyTorch. So in PyTorch, you have a module which is called a linear module, and this module has the following documentation that I screenshotted here for your convenience. And basically, it's a function that obtains as input the number of input features and the number of output features. So in simple words, you have W, which is of size input features times output features. And all you have to specify is how many input features and how many output features you have. Okay. And there's some more details, but I don't think they're very important at this point. And here's a simple example of how this looks in PyTorch, how you can create a multi-layer perceptor in PyTorch. So what you do is, first of all, you import PyTorch, and then you define a class MLP, which is an NN module. This is something called inheritance, but if you don't know what it means, it doesn't really matter. And then you define the different modules that you want. So notice what this does is, first of all, you define FC1, which is a linear model that goes from 28 squared to 500. Does anyone know why we have 28 squared here? Why would you expect to have 28 squared?
28 by 28, the size of the image or something?
Yeah, exactly. Thank you. It's 28 by 28. And because we vectorize the image, then it becomes a vector of size 28 squared, right? And then the next, the output number of features is 500. So this is an arbitrary number that you could choose to be whatever you want. The next, how to prune the connections. What does it mean, how to prune the connections? From one layer to the preceding layer. I'm still not sure I understand what does it mean how to prune. Upon training, can we get, so you can get zero weights and it doesn't prune the connections. No, it does not. No, unless you do, there's people who do research on how to prune networks, how to prune the weights and so on. So there are people who do that, but it's not part of the standard code. So the matrices are initialized. It's written here how they're initialized. In this specific case, they're initialized with a uniform distribution between minus square root of k and square root of k, where k is one of the number of input features. But you can actually change that. So the next thing we have here is a second fully connected layer. That is a matrix that goes from 500 to 256. And then we have a third fully connected layer that goes from 256 to 10. Why do we do 10 in the end? Because in this specific example, it's the number of classes, exactly. Yeah, 10 classes. Now, in addition to those linear layers, we also need the nonlinear layers. So this is the ReLU 1 and ReLU 2, which is simply defined as nn.ReLU. So this is the ReLU module. What does it mean in place equal to false? You can just ignore it, just useless text, okay? I mean, it does have a meaning, but for the sake of this course, it doesn't matter. You can actually even remove it. Now, all of this is basically defining a bunch of modules which are being saved in self. Self, you can think of this as the object. So you store in the object a bunch of different modules, and then you must define a forward function. The forward function is applying the network on an input X, right? So what do we do with an input X? So first of all, an input X is usually a tensor of size, number of images, times number of channels, times height times width. What does this mean? So imagine we're looking currently at 128 images from different classes. And imagine that we have images which are grayscale. So it's images which don't have color. So we have one channel. And imagine that all the images are of size 28 by 28, okay? Then what this line here is doing is it's reshaping, view just means reshape. It's reshaping your tensor of images so that it would be of dimension 128 by 28 squared. Does this make sense? I feel like this is a bit tedious, but maybe for people who haven't seen this is the bare minimum of what you should probably know. So, yeah.
Oh, would you repeat? Would you mind repeating what forward means again?
Yeah. So forward is going to essentially implement these equations of the forward pass. So it's just going to take an input X and then apply a bunch of linear layers and also nonlinear layers. Now, the only difference between this mathematical description and the network is that the mathematical description usually speaks in terms of a single input X, because it's easier to reason about a single input, whereas the network works in a batch. It's called a batch of images, many images together. So for example, here X would, after you reshape it, would have 128 images, each with 28 squared pixels. And then the next line takes X and applies the fully connected layer. And then the value, very simple, right? The next line takes, we assign that to X, and then we take X and we apply the second fully connected layer and the second value to get a new X. And then you apply the third fully connected layer, and that's it. Simple, right? Now, once we've defined this class of a network, which is called a multi-layer perceptron, we can initialize it. So here's the initialization. And we can pass a fake input. What is a fake input? A fake input is basically just passing garbage through the network. So instead of passing actual images, we're just passing some random numbers just to check whether it works, right? So what should be the size of the input? The size of the input is 128 by 1 by 228 squared. So I guess it should have been here 28, but it doesn't really matter. Now, notice that here it says torch rand_n. Rand_n is just a random number generator that generates from a Gaussian distribution with zero mean and unit variance. And after we define this, after we sample this input, random input, we can pass this random input through the model and calculate the shape. Now, what do we expect the shape to be? So if you took 128 images and you pass them through the network, what would the output be? I guess it's written at the bottom, but maybe we can cross it and think to ourselves. So one person says, Neo. Wow, that's super cool name. It's like Neo from the Matrix. It is, wow. I feel like I should steal your name from today. I want to be Neo as well. I never thought it's even an option to be Neo. It's just, oh, so back to the question, 128 times 10. And that is correct, yes, because you have 128 vectors and each one of them has 10 entries, right? So you get 128 times 10. Does this make sense, Neo? I'll never forget this name, Neo. Wow. Yeah, 128 copies of the logits, exactly. Okay, so this was our first network. Next, we're going to talk about something called convolutional neural networks. So before we talk about convolutional neural networks, let us gain some motivation in the form of a YouTube video. So if everyone can go to this link and watch the YouTube video for the sake of motivation. So what you can see in this YouTube video is a young Jan LeCun who is sitting in front of a computer, and next to the computer there is a scanner, which is basically a camera, and the camera is looking at different images which have digits on them, and the computer is running some type of a network which is called LeNet on these images, and it manages to identify what digits appear in the image automatically. So you can see towards the end of the video how the digits become, the digits are non-trivial in some sense because they don't look like standard digits. And you can see two of Jan LeCun's friends. Okay, so in that video, the architecture that Jan LeCun was using was not a fully connected layer. It's what's called a convolutional neural network. So what is a convolutional neural network? So here you can see a small depiction of what a convolutional neural network is. It's basically a network which has three types of operations. The first operation is a convolution, and I'll explain what's a convolution. The second is called pooling, and I'll explain what's pooling. And the third is, again, the nonlinearities. So let's start with what's a convolutional layer. So a convolutional layer, as the name suggests, actually, a convolutional layer does not do what the name suggests. What would you expect a convolutional layer to do? You would expect it to apply some type of a convolution, right? But a convolutional layer is actually applying autocorrelation. What's the difference between autocorrelation and convolution? Is there a double E person in the crowd who cares about the difference between autocorrelations and convolutions? No double E people in the crowd. The difference between a convolution and an autocorrelation is that in convolution, you have to flip the kernel. Whereas, yeah, order? No, it's in the convolution, you have to flip the kernel that you're convolving with. Whereas in autocorrelation, you don't. But that's just details. Let's ignore those details. So a convolutional layer, you can think of it in 4 different scenarios which have increasing complexity. So let's start with the simplest case where you have an input X. Let's imagine it's a one-dimensional signal. So one-dimensional input of some sort, like a vectorized image. I guess that one doesn't make sense, but it's a one-dimensional input, and W is a single filter, which is why I say single filter, right? So what does it mean for us to convolve X with a filter? Does everyone know what's a convolution? I should have asked. Is there someone? Oh, okay, so there's at least 2 people. 1 person, 2 people. Hold on. Yeah, it's discrete convolution, yeah. So basically, a convolution is you take a certain signal, right? This is a signal. And you take a certain, it's called, so this is X. And you take a certain filter W, which is usually of smaller, smaller support. And then you calculate the inner product. And then you shift W to a different location and calculate the inner product, shift W to a different location, calculate the inner product, and so on. So if I do a proper example, let's do a simple example to illustrate. Imagine that we have a piecewise constant signal that looks like this. Okay. And imagine that so this is X. And imagine that W is a step function. So it looks something like this, right? So what is going to be the result of the convolution? The result of the convolution is going to be, it's basically going to have a, let's see. So here it's going to be positive, right? Here it's going to be, I guess we should make this maybe negative. Let's do it like this. So this is like +1 and -1. So first it's going to, so this is W convolved with X, convolution. Convolution X. So first it's going to be positive, then it's going to be negative, then it's going to be positive, and so on. Oops. Does this make sense? So, oh, sorry, 1 second. So basically here you have a jump, right? Whenever you have a jump, you're going to have a positive, I guess, a delta, right? And whenever you have the opposite jump, it's going to be a negative delta, right? Does this make sense? Because if you're doing an inner product between W and the signal X at places which are constant, then it's just going to be 0. Maybe I should also make the W of smaller width, otherwise it doesn't make sense. So to the person who said that they've seen continuous version in real analysis, so it's basically the same thing, except it's discrete. And also the W has a shorter support, which means it has a bunch of zeros in it, right? Does anyone have any questions about the simple convolution? About the single filter, single input channel? Could you state the formula? Yes. So regarding the jump, basically, okay, let's just do the formula. So H at place, let's say, T is equal to sum of, and then let me shift this so it's more pleasant to look at. And then you do K equal to, let's assume that our filter is of size minus W. W stands, oh, I guess W is very confusing. What should we use? Let's say minus M, yeah, M to M. And then you have W at place M multiplied by X at place T plus M, okay? So you're taking X at place T and you add M, which goes from minus M to M. And you're multiplying by W. Maybe this figure helps. Let's see the figure. I actually don't know how to open figures. Oh, I do. Oh, yes. So do we take the indices of X mod M? Not in deep learning. In math, you usually do, but not in deep learning. So in fact, here T goes, so here, so you asked, do we take the indices of X mod M? So there is a different types of convolutions. There is something called circular convolution and non-circular convolution. So in circular convolution, you basically circle all the way. And it's, in circular convolution, you circle all the way. So your filter, if this is a signal of some sort, right, then the filter could be partly here and partly here, right? So in deep learning, you never have this. You don't do circular convolution. Does this make sense? Your filter cannot like circle around the signal, so to speak.
So I guess my question is H an infinite?
Oh, this should be K. Sorry. This should be K. Sorry, yes. Go ahead, please, yeah.
Is H an infinite vector then?
No, nothing is infinite in deep learning. Everything is finite. So H is a vector of size. You can think of it as size, you know, capital T or something, or N, whichever notation. Oh yeah. Sorry. Yeah. Thank you. Yes.
So then we're taking X to be of size big T plus 2M, right?
Yes. Okay. Yes, exactly. So if the index gets out of bound, then we just define W and X to be 0. Yes, that's one way to put it. Regarding the question about autocorrelation and cross-correlation, I need to refresh my memory about cross correlation, but as far as I remember, it's autocorrelation. Function on Z with finite support. Yes, you could say that. Yes, yes, yes. You adjust the size accordingly, finite but big enough. Yeah. So, for example, you know, in the case of you can think of capital T as being a signal, you know, of size 100, and the filter is a filter of size 3, for example. Does this make sense? So this is convolution with a single filter. Now, what is convolution with multiple filters? Did I answer all the questions? By the way, I feel like there were many questions. Does anyone have another question? Objections? Yeah, exactly. Non-circular convolution. Yeah. Okay, so what is convolution with multiple filters? Convolution with multiple filters, as it sounds, is just you take X and you convolve it with different WJs. So you have W1, W2, and so on. And as a result, you have different H's, right? So if we were talking about, let's say if you had an image, right? And if you apply convolution with a filter, then what do you get? You get an image, right? So in that case, it becomes 2D convolution. So how 2D convolution is the same thing as 1D convolution. You just, instead of shifting in one dimension, you shift in 2 dimensions. Does this make sense? So you can define convolution in 1D and also in 2D. I won't try the formula because I've made 2 mistakes in the 1D. So I guess it would be more mistakes in 2D. But in 2D, what would happen is that you have a filter, a small filter, and it's just shifting around the image, right? And you calculate different inner products. Does this make sense? See out. I haven't gotten to that yet. I'm still in the multiple filters case. So I'm still here. Oh, see out here. See out is the number of filters that you have. Now, so the way it's implemented in the software is that all the filters are just, you're doing this thing, right? So it's basically a small matrix of size, let's say 3 by 3. And you don't zero pad it because it doesn't make sense computationally to zero pad things, right? So when you ask about the support of, a filter in 2D, the support is, I guess, maybe, can you maybe explain more what's the question when you say what about the support of a filter in 2D? Oh, the size of the filter. So it's going to be M squared, M by M. So this is going to be M, and this is going to be M. Does this answer the question? Yes, it is always small. It's usually 3 by 3. That's the most canonical size. Yes. And the image is something like 20, 30 by 30 or 100 by 100. So the filter is very small. Now, if you apply a bunch of different filters to an image, each filtration, each one of those HJs is the size of the image, right? Because you're convolving an image with a small kernel, so you get something which is the size of the image. And you can then stack all of these outputs together, and you get a 3-dimensional tensor. So this is, here you can think of a slice here. A slice here is HJ. And if you stack all the slices together, you get the output of the multiple filters. So a filter is what I called W here. You can think of it as just a small vector or a small matrix in the case of 2D convolution. that could be massive impact on the memory depending on how large the layer is. Yes, it could, yeah. So Gina, that's the definition of, the filter is this W. So W is basically, it depends how you want to define it. There's many ways to define it, but it's just a small, you can think of it as a small vector, which are convolving with the input image through this equation. Yeah, it's like a subset of the image. So the next thing is multiple input channels. So let me clear this thing a bit. So if you have multiple input channels, it means that X is, for example, an image which has RGB. So 3 channels, right? So you have a channel, here you have 3 dimensions. Here you have the height of the image, here you have the width. Now, in this case, what would be the dimension of WK? So if you want to convolve WK with an image which has 3 channels. Yeah, so for example, it could be 3 by 3 by 3 because you have something like this, right? So the filter, let's say, is 3 by 3. And also it has 3 channels. So it's 3 by 3 by 3. A filter is always, this has to be the size of a patch from the image. What is C in? C always stands for channels. In means the input. So it's the number of input channels. Yes, 3 in this case, that is correct. Now, why are we doing a summation here over K? Does anyone know? Joan, that is correct. RGB image seen is equal to 3. So WK is 3 by 3 for a specific K, right? So WK for a specific K is 3 by 3. But if you look at all the W's together, right, then you get that this is in 3 by 3 by 3. Does this answer your question, Karen? I guess the way people in math like thinking about convolutions is through zero padding. I understand that maybe that's a source of confusion because in math they like zero padding the function and doing circular convolution and so on. But I want to present it the way that you would read it in a deep learning paper, so you can actually go out to the wide world and understand what people are talking about, you know. So someone says the formula is not exactly the same as the graph you draw. So in what sense is it not the same?
Because you're doing like 2 by dimension 2 convolution, like at each dimension and then sum them. But in the graph, like it looks like you're doing a dimension 3 convolution.
So the way to think about the graph is that this 3 by 3 by 3 chunk is only moving in the spatial directions. So basically, this 3 by 3 cube, let me illustrate the moving. Let's see, let's pick the move. Hold on 1 second. Yeah, so you see, I'm illustrating a convolution using this technology. So you start here, you shift the filter, shift, right? So it doesn't move depth-wise. So the person who asked the question, it's a sum of 2D filters, yes. But when you ask a person in the deep learning community, is this a sum of 2D filters? They would say, no, it's a 3D filter. The filter is a 3D tensor, right? you're correct that it's not a 3D convolution, because a 3D convolution would convolve in the third dimension as well. So Neo says, when you sum WK together to the different color do the different color layers collapse together? Yes, exactly. Yes, yes, they do. They do. So I guess I should have defined this. So XK, X1, you can think of this as the red channel of the image. X2 is the green channel of the image. And X3 is the blue channel of the image, right? And similar to WK, W1 is the red channel of the weight and so on. So now the output of this convolution is going to be what? Is going to be of the size of the input image, right? If I draw this, make it proper. Yeah, so the output is going to be the size of the input image. And now we have the case where we have multiple filters, C out filters, channel out filters. And so we basically stack a bunch of those things together and we get a three-dimensional tensor. So how many channels do we have here? C out. What is the height? The height is the height of the image. What is the width? The width of the image. How do we obtain this tensor? By taking our input X and convolving it, I guess 2D convolution and summing across the channels is how you would prefer me to say it. And notice here you have an index K, oh sorry, the index J, which is the index which specifies which one of the multiple filters we're looking at. Does this make sense? Does anyone have any objections? No objections. Karen, you have the most beautiful studio I've ever seen in my life. The lights and wow. I feel like my studio looks so bad. Let me change my background to something. Let's put me in outer space. It's just. Do you end up having better accuracy when you have more filters? That's a beautiful question that we will address in the following lectures. We will address that. That's a beautiful question. So hopefully you understand what a convolutional layer is. If you don't, you can always go to the PyTorch documentation and try to figure out what's written here. I assure you it's less clear than what was in the previous slide, though. But basically this equation here defines the output of the convolution. And yes, when you train a layer, you'll be training the filters. That's correct. Is there a way to visualize the filters? If these are filters in the first layer, then yes. I'll show you the filters in a future lecture. Regarding PyTorch versus Keras, let's discuss this at the end of the lecture. So the notations they use here are supposed to be the same notations as I was using in the previous slide. But what's important, this is the most important part to understand. Everything I said in the previous slide was assuming that we have 3 channels in the input in X, right? So R, G, and B. So essentially, we started with a 3-channel image, right? So this was 3, height, width. And then we applied a convolutional layer, and we got a 3-dimensional tensor, right? Which is, let's say here we have C out, which is, I don't know, 128. So this is still height and, oops, this is width and height. Now you can actually apply the same, you can apply a convolution again on this 3-dimensional tensor and get a new 3-dimensional tensor, right? The new 3-dimensional tensor is going to be something like, let me draw properly. So let's make it wider actually, something like this, right? So the height and the width are the same. And the only thing that changes is, let's say now we have 256 channels, right? So you see it's the same convolution as we did previously, It's just that instead of having in these formulas Cin equal to 3, in the next layer, you would have Cin equal to 128. Okay. So is it ever advisable? When you say share filters, do you mean between the layers? I'll talk about that in the last lecture of the course. This is an unexplored, somewhat unexplored question. That's a good research question. It's a good research question. I think that it's unclear at this point. At least to me, it's unclear. The next thing we're going to talk about is pooling. So pooling is much simpler. Pooling is imagine that you take this three-dimensional tensor that we had, and you take a certain slice out of it. So a slice is something like this, right? And you take this slice and you plot it. So this is how the slice looks like. Pooling is when you take neighborhoods of size, let's say 2 by 2, and you just replace them by either the maximum or the average. These are the most commonly used. So here we replace by the maximum, which is 6. Then we take the second neighborhood, which is the green neighborhood here, and you replace it by a scalar, which is the maximum, that's 8, and so on. Now you do this independently for each one of the slices or for each one of the channels here. So what does pooling do to this three-dimensional tensor? It changes the dimension so that in this case, the height and the width are going to be 2 times smaller. So it's going to be height over 2, width over 2, and the same number of channels. Does anyone have any questions about pooling? What's the advantage of pooling? So the advantage of, let's say the most straightforward advantage of pooling is that your tensor becomes smaller. So your computations become more efficient, right? It was found empirically that it's beneficial in terms of accuracy to increase the number of channels with depth and apply pooling to make the image smaller. How did W and H divide by 2? Because you replace every neighborhood of size 2 by 2 with a single scalar. It's not a learned parameter, Nicholas. And the answer to any question like how do we select something is always trial and error. Trial and error. Trial and error. I mean, Reza, yes, it is in some sense compressing the image by applying a certain function, yes. That is correct, yes, empirically observed. This is the field. Did I miss any question? So stride is how much are you, so notice that you have 2 parameters here, the size of the neighborhood and how much are you, what's the distance between the neighborhoods, so to speak. So here you jump 2 pixels, right? So this is stride equal to 2 and the window is equal to 2, right? Stride is how much do you jump with the neighborhood. Okay, so this is the documentation of the pooling layer. I guess this is also unclear, so let's skip it. So here's how it looks in practice. So this is LeNet 5, the network that we saw Jan LeCun use in PyTorch. So how does LeNet 5 look? So you, again, define a network, which is called the net5. And then you define the convolutional layers in a sequence. And then sequential just means a sequence of layers. You can think of it as a list. tanh is a nonlinear function. So here you can see tanh. It's a nonlinear function that is rarely used in practice, but in this case, I wanted to show you the original net, which used something similar to a tanh. Now, what's more important is notice how the definition of the network looks like. So we do conv2d, so create a convolution that takes as input one channel, because it's grayscale, and outputs 6 channels. What does it mean, 6 channels? It means that we have 6 filters that are being convolved with the image. So we get a tensor of width 6 in the output. Does this make sense? 6. So if you start with an image of a single channel and you apply this convolution, you would get a 3-dimensional tensor where here you would have a width of 6. Now, the next thing we do is tanh, which is a nonlinear function. Oh, I didn't specify. Here, kernel size is just the size of this W that I mentioned earlier. In this case, it's 5 by 5. And stride equal to 1 means that you shift the filter W by a single pixel every time. No, this is a different stride. This is the stride of the convolution, which is by how much does the filter W move. In math, usually the filter moves continuously, or if it's discrete convolution, it moves by a single pixel, so to speak, right? Or a single entry at a time. But in deep learning, you can move the filter by more than one place every time. The kernel does not have to be square, but in practice, everyone uses always a 3 by 3 square kernel, 99% of the time. Won't the values saturate? Many crazy things can happen. And basically the art of training a network is to avoid those things, right? So you need to initialize the network in a certain manner. People have developed tricks over many decades, and those tricks are are targeting different issues that might emerge, like saturations and so on. PyTorch does not handle in any specific way the saturation of the finite representation of digits. So let's continue with the network. So the next thing we have is average pool with a kernel size of 2. So that means we're averaging every 2 by 2 neighborhood. And then we have a convolution again, which obtains as input 6 channels and outputs 16 channels. So we get a 3-dimensional tensor now, which has 16 channels, right? And so on. So then you have tanh, average pool, convolution, tanh, and then you have a different sequence of layers, where in this case, you're using fully connected layers. So you start, so this is again back to WH plus B instead of, convolution of W and H, which is what these layers are doing. So we have a linear layer, then tanh, and then another linear layer. And the forward pass here is basically you take X, you apply all of the convolutional layers. After you apply all the convolutional layers, you reshape it so that you have something that is of size batch multiplied by something. When you write -1, it means whatever it is. So X is of size batch times what? Times the number of output channels, 120, times H times W. Does this make sense? So this is the output of X after you go through all the convolutional layers. Because, so the answer to Gina's question is the answer to most questions, which is that it was proven empirically to be beneficial. I feel like I'm in a court of law, you know, and I keep repeating the same statement. It was proven empirically beneficial to increase the number of channels with depth. As far as I'm aware, there's no reason why that would be, you know, there's no theoretical reason. Yes, you should, because it was empirically proven to be beneficial. Yes, that is correct. But I don't want to digress to different architectures like Glow. You can ask about that in the end of the lecture. So basically you take X, which is a stack of images, you apply all the convolutional layers, and then you get 120 channels, and then you apply all the fully connected layers, and you get the output of the network. So hopefully this makes sense. And this is a simple example of a simple architecture. I have a set of illustrations that show what is happening in a convolutional layer. So there is this person who worked really hard to create an illustration of what the layers of a convolutional neural network are doing. So I thought it might be beneficial to look at those illustrations. So here what you see, this is the input image. And then here you can see the first layer features. This is the second layer features, third layer features, fourth layer features. Here you have fifth layer features and sixth layer features until you reach the final layer, which has 10 entries. It's a 10-dimensional vector. And you can see that currently it's lit up on the 8, which means that the image is classified as an 8. So let's look at what the layers are doing. So first you have the input layer, which is the input image. And you can look at every pixel and, you know, evaluate what is the gray level. I guess in this case, it's not really gray, but whatever. The next thing you do is you want to calculate a convolution, right? So what if you can see what's happening here is you have these lines. Do you see the lines? Different lines. Hopefully you can see the lines. Oops. And the lines are looking at a certain neighborhood here, and they're taking this filter and they're doing an inner product with the neighborhood and giving you a certain value here. So in simple words, what's this image? This image is the result of convolving the input image with this kernel, with this filter. Filter and kernel are synonym words in this discipline. Does this make sense? So each one of these images is the convolution of the input image with a different W, with a different filter, right? So just to test your understanding, how many filters were used in the first layer? I think it's actually six, yeah. Okay, and next we move to the second layer. So here you can see again, do you see these small things, so this is a downsampling layer, which is doing max pooling. So we take a small window of size 2 by 2 and replace it with a single scalar, right? Next, we have the next layer. So the next layer is doing, this is already becoming a bit complicated. So what's happening here? You're looking at a neighborhood here, at a neighborhood here, at a neighborhood here, at a neighborhood here, here, and here, right? And you're doing a dot product between all of these windows with certain filters, and then you sum everything and you get this value. So earlier I wrote the equation sum over WK convolution xk, right? And the sum was over k from 1 to c input. So in this case, c input is equal to 6 because you have 6 different things here, right? And those wk's, this is w1 here. I guess w1 is what's dot producting this first neighborhood. W2 is what's dot producting the second neighborhood, and so on. And this sum is exemplified by the fact that everything converges to the same point, right? Does this make sense? Is this illustration useful, or is this just confusing and a waste of time? I thought this person, you know, probably wasted a week of their life creating an illustration. And I thought we should respect that person by looking at the illustration, right? And enjoy it. So the number of channels is like how many images? Yes, yes, yes. But don't get confused, Gino. The number of the images are the different slices or the different channels of a 3D tensor, right? So basically, you could take all of these images and stack them together into a 3D tensor. Does this make sense, Gina? But what you said is correct. The number of channels is how many images you have. Yes. Channels are kind of like imagined colors. Exactly. Yes, yes, yes. Okay, so now we have the next layer. So here you can see, what does it say? It says downsampling with max pooling, right? And so we can see how we're taking a 2x2 neighborhood, and we're replacing it by a single scalar here, right? Notice how this downsampling is only done on a single channel, right? It's not doing pooling across channels, only spatially. This is a single channel, right? Okay, so this is now another, so this is, the naming is a bit confusing, but this is a fully connected layer. Why is it a fully connected layer? Because essentially, if you take all of these things, right, and you construct a vector and you think about, let's denote this by, you know, H or something, and then you multiply H by a matrix W, right, then it's equivalent visually to, and you look at the certain entry of this, let's say the kth entry, then this is the kth entry of this matrix multiplication, right? You can think of matrix multiplication as a bunch of edges going into a single scalar, which corresponds to the entry at the output of the matrix multiplication, right? This is another fully connected layer. You know, why is it called fully connected layer instead of matrix multiplication? You might ask yourself, because you can see everything is fully connected, right? And finally, we have the last fully connected layer, which goes to the logits. And you can see how there's a single logit which is bigger than the rest, and that's the logit of the class 8. Okay. So this is the end of the illustration. So far we talked about LeNet, which was an architecture. Oh, there's a question. In this case, if we choose ReLU instead of tanh, would it work better? You cannot know without trying. You should try. Run an experiment. It was found empirically that ReLU is the best nonlinearity to be using. Nonlinear functions is hidden inside a fully connected layer. No, it's not. It's not. But in this visualization, they're not showing the nonlinear function. So in this visualization, it is, but in PyTorch, it is not. Does this answer the question, Amireza? Okay. The second conv layer seems to discard some of the previous layer slices. Is this by design? The second conv layer. Let's look at the second conv layer. So this is the second conv layer. And why are you saying it's discarding some of the channels? Oh, it does seem to be discarding. Oops, let me just. That's a good question. I'm actually not sure why it's discarding. I think maybe it's either a bug with the visualization or I don't know. But it does seem like there should be more edges here, right? That's what you're saying. There should be more edges. I don't know why there are no more edges. How does someone come up with this? It is not intuitive at all how this works. You just sit in front of a computer for a very long time. Can we gain insight as to what features the filter is? I guess when you say this is non-intuitive, do you mean the convolutional part or the whole thing? The whole thing. A lot of this is inspired by how people believe the brain works. So I think people do experiments in neuroscience and then try to imagine how to translate that. Yeah, I think that's a non-trivial idea. Yeah. Yeah, it is non-trivial, very non-trivial. Can we gain any insight as to what features the filters are pulling out by looking at the filter visualization? The filters, it's easy to visualize filters in the first layer. But if you look at deeper layers, visualizations are a bit more tricky, but you can do that. Yes, you can do that. You can do that. I think in the next lecture, I'll show that. Okay, so far we talked about a simple architecture, which is LeNet. And in 2012, these students, PhD students from U of T and Professor Hinton wrote a paper about ImageNet classification with deep convolutional neural networks. Essentially what they've done was use a network which is very similar in some sense to LeNet on the ambitious data set of ImageNet. So you remember we've seen the ImageNet data set in the previous lecture, or I guess previous, right? So here you can see the how the architecture is built. So hopefully by now this image doesn't scare you too much. What's happening here, this is the input image. You can see the number 3, which means that it's 3 channels, RGB, because ImageNet has colored images, right? And you can see how they write the number 224, which means that the input image has height of 224 and width of 224. You can see how they have this thing here, which is a filter, right? And you can see how they write the number 11 to indicate that there is a filter of size 11 by 11 by 3, which is the number of channels. And then they do these edges to indicate that this creates a neuron. This is called a neuron in the next layer, right? Then they do max pooling. So in the max pooling, they take a window of size 5 by 5, right? And replace it by a single neuron. After the max pooling, they have, I guess the first thing was convolution. The second thing is max pooling. This is, I believe, convolution. I don't know why they're using the word max pooling here, but there's no 2 consecutive max poolings. Oh, maybe what they mean, sorry, I think what they mean is that this is a convolution with a 5 by 5 filter, and in between you're doing a max pooling. And then you have a convolution with a 3 by 3 kernel. And at this point, you have 128 channels. So you have a filter of size 3 by 3 by 128. So this is Cin equal to 128. And then you have in the output 192 filters, right? So that's why you have here 192 and so on. So you repeat basically convolutions and max poolings until a certain depth, and then you just apply dense. Dense means fully connected. or how a mathematician would call it, matrix multiplication, affine function, right? So you have one affine function, two affine functions, three affine functions, and in the end you get 1,000 entries which correspond to the 1,000 classes in ImageNet, okay? Now there's more complications here. You can see this thing here, but I don't want to go into that. It's not important at this point. So in their architecture, they used some module, which they used a module beyond the convolution pooling and fully connected, something called dropout. But I think I'll skip it. I don't want to talk about dropout. And essentially, the AlexNet architecture had many hyperparameter. What do you mean by this is the opposite of you mentioned? What? Okay, it seems like people want me to talk about dropout. I think I'll skip dropout because there's little reference throughout the course to dropout. So the next architecture, it does increase. So you start with 48, then you have 128, then 192, 192, and eventually the fully connected have 2048. Oh, I guess here it does decrease, you're correct. But for the most part, I mean, since then there have been infinite architectures that came out, and it's very, very canonical to increase the number of channels. You know, nothing is set in stone, right? Just ignore the boxes upstairs. Just ignore them. Not important. Oh, okay, so the next important architecture that you should know of is called VGG. So basically, VGG was written by, this person is a very, very renowned computer vision person. And basically what they said was there's too many hyperparameters in AlexNet, meaning that the size of the filters are different, the number of channels are funky, and so on. So they said, let's do something more standardized. And so they proposed this architecture that you can see here. So here, each one of these is a different architecture. So the way you read it is, let's say here, it says 19 weight. It means 19 layers. And then the first layer you have is a convolution with 64 filters. The second is a convolution with 64. And then you apply max pooling. Then you have a convolution with 128, convolution with 128, and then you apply max pooling. Then you have a convolution with 256, 256, 256, 256, and then you apply max pooling. Then 512, 512, 512, 512, and then you apply max pooling. And then you have 512, 512, 512, 512, and then you apply max pooling. And then you have fully connected layers. So what's the big difference between this and AlexNet? The big difference is that they use 3x3 convolutions instead of 11 by 11 or 5 by 5 and so on. All the convolutions are 3x3. And you can see how the number of channels is, it's much deeper. Yeah, it's much deeper. And you can see how the number of channels is a power of 2. Why is the number of channels a power of 2? Because computer scientists like powers of 2, right? So it's 64, 128, 256. So conv3, I believe, means convolution of a 3x3 filter. So if you look at the AlexNet architecture, you can see how first the number of filters is, here it's 11 by 11, for example. Then it's 5 by 5. Then it's 3 by 3, 3 by 3, 3 by 3, right? So in VGG, they just said, let's have 3 by 3 always. LRN. Do you mean in AlexNet or do you mean in the VGG? On this slide, LRN. I don't see LRN. LRN. Oh, LRN. I think I know what it is, but just ignore it. Doesn't matter. There are certain things that are no longer being used, so it would be a waste of time to discuss them. We're taking convolutions of the image with a filter. In the first layer, it's a convolution with the filter and an image, but in later layers, you can think of the tensors as being an image with many channels, right? Yeah, it is local response normalization, yeah. So this is a different visualization of the network. So there's something called block. Block means that blocks are differentiated by a max pooling layer. So each time here you have, I guess it's written here. So you can see the max pooling, max pooling, max pooling, max pooling, max pooling. So each time you have a max pooling, it's defined to be a different block. And you can see again, the first layer has convolution, 64 channels, convolution, 64. Then you have convolution 128, 128, 256, 256, 256, and so on, right? So this is just a different visualization of the architecture. In the previous slide, it was in the form of a table. Now it's in the form of a drawing. Here is a different visualization. Is the thickness of the result of convolution implicit here? Say in the multi-filter case. Yeah, you cannot see the thickness here, I guess. You cannot see the thickness. But because you know that the, instead of drawing a tensor, which is 64 channel thick, you can just say convolution with 64 filters, right? Which is what they're doing. Does this make sense? Ideally, you would also say what is the number of input channels, but you can just infer it based on the previous layer.
Sorry, where do they list the thickness of the convolution?
Oh, here you see 64. 64.
Isn't that the dimension of the matrix? Isn't that like one side length?
I guess you cannot really tell based on this drawing, but I would say it's the number of filters in the convolution. I would say that. Yes, it's the number of filters. And you can infer how many, what's the side length, as you called it, of the tensor just by looking at the previous layer. Because if you have if you have here 64 filter, or let's say here, if you have 64 filters, then the number of input channels to this module has to be 64 as well. So someone asks, I think we map to a fully connected near the end of the arcs to classify the image, but if we wanted to say replicate the image, could we apply the filters in reverse? Replicate the, what does it mean to replicate the image? Oh, generate. So there's works that try to generate the original image, and just, in some cases you can, in some cases you can't. You can solve an optimization problem that would try to replicate the image based on the output. Basically, the way it works on the edges is, let's say this is our image, then the filter cannot escape the image, so to speak. So if this is the image and this is the filter, you cannot have something like this. So hopefully this answers. So in reality, what people do is, if you just apply the convolution as is, then you see how the size of the image would shrink slightly, right? Because if you convolve an image of size let's say n by n, with a 3 by 3 filter, the size of the image would decrease by 1 on each side. So in practice, what people do is before convolving, they add a padding of size 1 of zeros. And as a result, after the convolution, the size of the image does not change, stays the same. So that's what the person was referring to as padding. So this is a different visualization of the network. People like visualizing it in different manners. This is another way. So you can see here the input image has 3 channels. We apply convolution here and we get to 64 channels. Then we apply max pooling, so the size of the image decreases, right? And after we apply max pooling, we have another convolution that takes us to 128 channels. Then you have another pooling here that decreases the size. And then you apply another convolution that takes you to 256 channels and so on. I feel like I've never answered Gina's question. Gina, what's the answer to your question sufficient? You were asking, we're taking convolution of the image with the filter.
Yeah, you answered it. And then you said afterwards, it's not the original image, but of the filter.
Yeah, but is the answer clear, I guess, was what I was wondering.
I think so. So are we convolving with different filters?
Yes, different filters. Each layer has its own filters.
Mm-hmm. Okay, thank you.
Okay. Yeah, so this is a different drawing. Now, after VGG, what happened was that there was a very big discovery by researchers in Google who realized that it's beneficial for whatever reason to normalize the features in the network. So imagine you take the features after the first fully connected layer, right? Which we denote by Z1. What is the dimension of Z1? So Z1 is of size batch times the number of channels times height times width. But because it's a fully connected layer, then I guess there's no channel height and width, so it's just some scalar, I guess. So it's, let's say it's just 28 squared for simplicity, okay? The first fully connected layer obtains as input a batch of images, each has 28 squared pixels. Now, what those researchers said is they were suggesting to do the following. They said, take all of these features, Z, and calculate the mean and the variance of the features per each entry. So let me visualize this. So here's Z, which is this Z, right? And each, let's say, column here corresponds to a different image in the batch. And each row corresponds to, let's say, a different pixel in the image, right? Oh, I guess after the first fully connected layer, it would be something like 64, right? Because this would be 28 squared, but here you would have something like, let's say 128. So let's be consistent, sorry for the confusion, 128. Now, what they said was, let's define a mean and a variance, which are being calculated across the batch for each one of these rows, right? So you're calculating a mean and a variance. So here's the mean. You take all of these Z and you average over I, which is the indicator of the image in the batch, and you get a mean, and you do the same thing, you get the variance. And then what they suggested was take your Z, which are the features, subtract the mean, and divide by the standard deviation. The reason you have this epsilon is because you don't want to divide by 0, so you add some small constant there. So to those of you who know statistics, what is this thing called in statistics? Trivia question. Does anyone know? What is this in statistics? So in statistics, this is called a z-score, a z-score. Now, after you take these features z and you normalize them, we get z hat. Hat stands for normalization. And the next thing they said was, let's take this z hat and multiply it by a scalar and shift it by a scalar. So basically apply an affine function. So basically you take a bunch of features, right? Calculate the mean, calculate the variance, subtract the mean, divide by the standard deviation, and then you get something which has zero mean and unit variance. And then you apply an affine function. Now, this sounds very, very strange. Does anyone know why it sounds very strange? Or is the description clear, first of all? So I can write it mathematically as z is in R, let's say P times B, where B is the batch. So the mean is just going to be equal to z multiplied by a once vector divided by B. Yeah, it is here. Yeah. So that's, for example, the mean, right? So why is this description strange? Does anyone know what's strange about this? So what's strange about this is you're starting with a z, then you're subtracting a mean and dividing by a standard deviation. So you get something which has zero mean and unit standard deviation. And then you're essentially ruining it, right? By applying another affine function. Doesn't this sound strange to you? No, it's actually divided by B, not P times B. By B. Because the mean is per each entry in Z. It's not a mean over all the features, if that makes sense. So in some sense, this is a strange thing to do because you're essentially, normalizing your features and then you're ruining it by applying an affine function. But it was shown to be, again, empirically beneficial. And the reasons are, I would say, unclear to this day. Why does it work? I should mention that this gamma here and this beta, which is the affine function that you apply, are learned parameters, right? So they're being learned by the network, similar to how the weights are being learned through backpropagation. So here's the documentation in PyTorch, which is, I think I'll skip it. No, not good enough. So the next thing I would like to discuss is ResNet. So ResNet is a different important architecture. So we had MLP, we had LeNet, we had AlexNet, we had VGG, and now we have ResNet. So ResNet is a paper that came out in 2015. And this paper was, I think, a significant mark in terms of the performance because it managed, I think this was the first time that these networks have managed to surpass human classification performance. So they reached 3.57 error. Human error is somewhere around 5%. And in this paper, what they suggested was instead of doing the standard thing that was common prior to that, of applying convolutions, ReLUs, and so on, they suggested to add something called a skip connection or an identity. So mathematically, what does this mean? So here, what you're doing is you're doing W2 on top of sigma, on top of W1, on top of X, right? Let's ignore the biases for now. On the right, what they're doing is they're doing X plus W2 times sigma W1 X. So do you see the addition of X? Now, why would you do that? What's the intuition? First of all, the answer is always because this works empirically. But okay, you're already nodding to this statement. But the intuitive reason is that think about the weights that you are learning, right? On the left, the weights have to learn a certain mapping from X to the output. On the right, the weights have to learn a different mapping, because you're essentially, you don't have to represent X in the output. You only have to represent the difference from X, so to speak, only the discrepancy from X. If this intuition doesn't make sense, then just ignore it and think of it as a trick that was found to be, beneficial for some reason, because it empirically worked. So is the definition of a skip connection clear? Does anyone have any questions about the skip connection?
A question. What is the delta thing?
The delta thing.
The
Which
triangle.
Triangle. Oh, that's, you mean the sigma.
Oh, the sigma.
That's the ReLU nonlinearity.
Oh, I see.
So you
Yeah,
see
makes sense.
here they have the conv, ReLU, and conv. And on the right, they have conv, ReLU, conv, which are by the way, I'm representing the convolution by matrix multiplication. The reason is that you can think of a convolutional layer as being equivalent to a multiplication by some very structured matrix. So for example, for those of you who know what a circular matrix is or a Toeplitz matrix is, a convolution can be written as a matrix vector multiplication through a Toeplitz matrix. Okay, so here you can see a depiction of VGG19 together with ResNet. So this is ResNet. And what you can see is that the main difference between the ResNet architecture and what they call a plane architecture is just the skip connections, right? So you just add these skip connections and that's it. That's the whole difference. And this dramatically improves the performance empirically. Now, notice again that at this point in 2015, people have already converged to choosing the hyperparameters in a very systematic manner. So you start with 64 channels, then you have here 128, then you have 256, and then you have 512, right? And I guess the only hyperparameter left is how many times do you repeat the convolutional layers. So here's, a certain number, here is much more times. So that's still a hyperparameter you need to tune. When I say hyperparameter, I mean something that cannot be easily differentiated. You cannot learn it using gradient steps, so to speak. And the last architecture I'm going to talk about is called DenseNet. So DenseNet is an architecture where the authors said skip connections are good for optimization. Why don't we add many skip connections, right? So they defined a DenseNet block, it's called, where basically you have a skip connection from every convolution to every convolution. Do you see this? Skip connection, skip connection, skip connection. Skip connection to everything. And so this is what they call a DenseNet block. DenseNet block. How does it affect the generalization error by passing the image itself to next layers? It improves the generalization error. It makes it smaller. That's why people are using it empirically, because they run an experiment, they add a skip connection, they see smaller errors, so they say good. Does this make sense? If the generalization error was worse, then people wouldn't use it. Are we going to talk about transfer learning? I think possibly next lecture, possibly. So here you can see a zoom in on the DenseNet block. And essentially the only thing to understand here is that you have many skip connections. And this is how the architecture looks like. So basically you have this DenseNet block, then you have another DenseNet block, you have another DenseNet block, and in between you have pooling layers, pooling, and that's it. Oh, I guess that the last thing is a fully connected layer. So I don't want to go too much into detail about these architectures because how do you know if your neural network is an overkill? So what you do is you train a network and you track the performance as function of depth. So if you have 100 layers and you get 5% error, and with 200 layers you get 3% error, then you go to more layers. So you can create a plot. Here you put test accuracy, and here you put layers, right? And you can see, for example, if it behaves like this, or if it behaves like that. Does this make sense? So the answer to your question is empirically. Okay, so this is a description of the DenseNet layer, but I think I'm going to fix it, skip it, sorry. So here you can see the performance on the ImageNet data set as function of years, right? So here you can see AlexNet, which we mentioned. You can see here ResNet, which we mentioned. And VGG was somewhere here. So this is VGG. And you can see how this is the human error rate, which is somewhere around 5%, right? And here you can see the big difference that AlexNet has made. So in 2012, the U of T team showed that you can improve the error by a significant margin compared to the previous year by using deep networks. And this has led to the revolution. So this is a summary of what we've seen today. And are there any other modern architecture that you think are interesting? I guess there's many architectures that I think are interesting, but the goal of this course is to discuss interesting phenomena in deep networks, right? So it's not really important. The details are not extremely important. What's important is that there is an architecture which is working extremely well, and we're trying to understand what is this architecture doing, right? So you have this huge, 100 layers in an architecture, which are taking your input image and transforming it in some manner throughout the different layers. And you're trying to understand what exactly is this architecture doing throughout the layers? Or can we say something about properties in a specific layer, right? And so because of that, we don't actually need to know all the different architectures. It's enough for us to have a few architectures and to study those architectures. Does this make sense? There are other modern architectures that are interesting, many, specifically now in natural language processing, LSTMs, I guess, yeah. Okay, so this is the end of the lecture and I'll stay for questions. Thank you very much for joining this week.
Sir?
Yeah.
Are we going to have the PyTorch assignment this week, and how exactly does it work? I'm not sure I understood.
Possibly you'll have this week, possibly. I haven't decided yet when I'll release it, but basically the assignment is going to be probably a part of, you get like some piece of code, right? And you need to insert a few lines that are missing there, right? So for example, I give you a piece of code where there's a layer missing, and because of that layer, the network won't run. Or you need to run the code so that it produces a reasonable error by tuning some parameter, something like that. Does this make sense?
Yeah, sounds good. And would we get like a more detailed instruction on how to set things up and stuff when we get the assignment?
Yes. But
okay.
I mean, it's basically you use Colab to run the experiment, right? And I mentioned Colab in the previous lecture. So if you want to, do something in the meanwhile, you can try to see Colab, like go to the website and see if you can connect to a GPU or something like that.
Sounds good. Thank you.
Okay. How much improvement is due to architecture versus other factors? It's actually all due to architecture, because the optimizers that are being used throughout the years are actually the same optimizer. There are new optimizers that people are proposing, but if you look at all these seminal papers, VGG, ResNet, DenseNet, the optimization procedure, the optimization protocol is basically the same. What about the computational substrate? So the GPUs are being improved, but if you look at these papers, the networks are always trained for something called 90. There's something which is called an epoch. An epoch is one pass through the data set, right? And 90 epochs means that you pass through your data set 90 times in your training. So this will become more clear in the next lecture, but essentially these networks are trained roughly to the same, roughly for the same amount of gradient steps. And so I think they're very comparable in that sense. And if you have a GPU, a faster GPU, it means that you can finish those 90 epochs faster. But it's not like one network is trained for 100 epochs and one is trained for 1,000. Some of the training accuracy is lost due to the type, which is determined by computational substrate. Do you mean like using, float? But all of these networks are trained with the same floating point, 16 floating points. Yeah, I think it's 32 floating point, not 16. It's 32 floating point. So there are people who are doing research on this question that you're asking, Nicolas, and they're trying to figure out if you can train what's called quantized networks. And the idea there is that you want to use less bits per each entry in your weight matrices. So the answer to your question is that that's a research question that's being researched by people. I would say you don't need all of it, but if you use lower precision, the optimization becomes significantly harder, which is why people are researching this topic. Does this make sense? So it will affect the performance, yeah. What was the big breakthrough? If you used lower precision, it would affect the performance, but all of these networks were trained with the same precision. That's what I was saying. What's the big breakthrough for AlexNet using deeper network? I think it was an amalgamation of different things. One thing was that they went for the biggest challenge out there, which was ImageNet. So ambition is always important in life. Should always be ambitious. The second thing is they used the ReLU prior to that paper. I think ReLU was, I think that was one of the big things that allow them to do the optimization efficiently, they used, I think the GPU factor was the thing that really, basically they implement, in 2012, there was no PyTorch, right? So you had to hack away your CUDA library to do convolutions efficiently and so on. So I would say that the big breakthrough that they had was due to really, really good coding skills by the authors. That's my interpretation. But it's also, the value that wasn't really used, the dropout that they added. It's a bunch of small things, but if you add them together, it makes a huge difference, right? Yeah, I tried coding CUDA. I wouldn't suggest this to people. Not for the soft-hearted.
I have a question, if it's
Mhm.
all right.
Yeah.
So with DenseNet, if we're trying to compute the gradient, first, is computing gradients at a certain point even useful? By hand, I mean. So
No.
Okay, because in the DenseNet case, it seems kind of annoying. I smell some inverse function theorem stuff.
Yeah, so basically the main use of PyTorch is what's called auto-differentiation. And auto-differentiation is this amazing capability. I'm going to discuss this in the next lecture, but I can discuss it briefly now because you asked. So imagine you define a variable in Python x equal to 1, y equal to 2, z equal to 3, right? And imagine you start calculating things like x plus y multiplied by z divided by 5, multiplied by z again, multiplied by x to the power of 3, right? And then you set this and you call this variable, out. The beautiful thing about PyTorch is that PyTorch can calculate d out to d whatever you wish, like let's say x, automatically. So you don't actually need to calculate anything. Your software calculates the derivatives automatically.
Right. And do they do this by some some numerics black magic?
No, it's not numerical gradients. It's actually, if you think about, what does the chain rule tell us? The chain rule tells us that if you have a bunch of boxes, let's look at some boxes. The chain rule is saying that if you have a bunch of boxes and you're interested in calculating the gradient, all you have to do is implement the gradient of the smallest box that you have. So for example, if you have a convolutional layer, you need to implement the gradient of a convolutional layer. You need to implement the gradient of a pooling layer. You need to implement the gradient of a ReLU, of a plus sign, of all of that. And PyTorch does all of that for you, right? So you don't need to implement any gradients. You don't need to implement anything. All you have to do is just apply all of these convolutions, poolings, ReLU in whatever way you feel like, because you think it would lead to the best performance, right? And then PyTorch is able to calculate the backpropagation automatically because it literally uses chain rule and the fact that it implements the derivative of a convolution, pooling, ReLU, and so on. Does this make sense?
Yeah, cool.
I'll discuss in the next lecture how this happens. It's basically one line of code. It's all you need. Can you talk about using PyTorch versus Keras? So my impression of PyTorch is that it's much more friendly than Keras. I don't use TensorFlow too much, and I find TensorFlow to be unfriendly. And I associated Keras with TensorFlow. I guess you can use Keras with PyTorch, right? There's, if I remember correctly. I haven't used Keras for a very long time, but the reason I prefer PyTorch and not Keras is because I think if you want to make an addition, like if you want to invent some new layer module, make a modification, and so on, it would be much easier in PyTorch than in Keras. That's my reasoning. Do you really like Keras?
No, I was just curious, mostly.
I tried it. I didn't particularly like it. I think it would actually suit this class because it's very easy to use Keras, but it would always be a disservice, to the students to teach them something that's easier to use, because it would be much harder for them to switch to PyTorch later.
But I mean, like, do you know which one the industry uses the most?
PyTorch, without a doubt.
Oh, okay.
And TensorFlow, but not Keras. I don't think anyone uses Keras.
Okay.
Keras is basically doing wrappers around things, right? It's a wrapper. So if a person is working in the industry on a project, they don't want wrappers because wrappers are preventing you from freely changing your code as you wish. Does this make sense?
Yeah, thank you. It makes a lot of sense.
Okay.
Are we gonna have a chance to talk about TPUs?
No.
Damn.
Is there something you want to discuss in this specifically about TPUs?
Just how the actual hardware allows for fast linear algebra. Like, it's sort of mysterious to me.
Actually, I never looked into the differences in the hardware between GPUs and TPUs. I think it's an interesting topic. There's many people who work on startups on the topic. And I think it seems like the current trend is that people are making specialized hardware that's somehow, if you restrict yourself to certain operations, you can really, take advantage of that.
Right. Yeah, I worked at one of these startups.
Okay.
Migrating
Yeah.
over.
Okay, so you know better than I do.
Just the speed gains, not any of the theory.
So there's like tricks probably. If you just use, conv or something, then you can probably speed up the convolution somehow. No? What was your company doing? Maybe you should tell us.
Oh,
This is being recorded though, so if you're gonna get sued, then maybe you should.
No, the company works on interpreting doctors' notes. I don't know if you know about medical coding, but the idea is to turn doctor notes into insurance billable codes automatically, and so lots of stuff there.
Sounds useful.
Yeah.
But isn't medicine free in Canada? So I don't understand the concept of a bill.
I worked. The headquarters were in San Fran.
Oh, okay. I see. Yeah, that sounds very useful though. So it seems like there is no more questions. So you translate, is it like OCR together with you need to interpret the text?
It was mostly raw text.
Mm-hmm.
So yeah, I mostly was more involved in like migrating the existing net over to TPUs. So like I didn't get my hands too dirty in the actual model, more just padding things out because TPUs really don't like dynamic allocation.
Yeah. Yeah, I tried doing TensorFlow with TPUs at some point. And I was talking to Google representatives as part of this effort. And they told me, like, don't change anything in the code. It's highly optimized. It will ruin everything. Did you get the same? Yeah. Like you said, it's highly optimized for, highly non-optimized, you said, for dynamic allocation, right?
Right. And we actually had to do a bit of hacking and slashing of the Google code, but
yeah,
pretty horrible.
Yeah, that was my experience as well. I had some very little experience. I was trying to speed up something, so I said, let's use TPUs. It's not as not as friendly, it seems.
It's not. I mean, it's funny though because they're very cost efficient. Like
Mhm.
they're fast, but also the price per minute or something is pretty low.
Mm,
So,
yeah. Hopefully they make it more user-friendly in the future.
yeah, all things Google Cloud. Don't even get me started.
Yes, yes, yes. Okay. Okay, goodbye. Bye-bye.
Thanks.